This is Algebra 1B, section 6.1, day number 2, and we're raising a power to a power. And to get an idea of how this works, we're going to do the same kind of process we did in the first day of section 6.1. So first example is worked out for us. If you're taking 2 to the third to the fourth power, that means you're multiplying 2 to the third by itself 4 times. And then using what I know from the previous section, because these all have a base of 2, I'm going to keep that base of 2, but then add the exponents, 3 plus 3 plus 3 plus 3, which is 12, so we get 2 to the 12th. And notice it says exponential form, so I'm not going to use my calculator to see what number that ultimately is. All right, second example, x to the fourth squared. What does that mean? It means you're taking x to the fourth times x to the fourth. You write it down twice. You're multiplying it by itself. There's 2 of them. And then as I look at these 2 terms, do they have the same base? Yes. So when we multiply them, we keep that same base. It didn't change. The base is still x. Add the exponents, and we get x to the 8th. For the next one, it says x squared y cubed. So we're taking x squared y times x squared y times x squared y. Now we have 2 different bases. There's both an x and a y. So I'm going to look at the x part of this first. X squared times x squared times x squared. Those things can be multiplied. Those blues all have the same base as x. And remember, when we're multiplying with the same base, we add those exponents. So 2 plus 2 plus 2 is 6. Then we have y times y times y. Those all have the same base, and that base is y. There is no exponent written up here, but it's an implied 1. So 1 plus 1 plus 1 is 3. And there's our exponential form for this one. A couple more examples of doing this really the long way. 2x cubed times 5. See if you can write out what that means. Write it out in the expanded form. So writing 2x cubed times itself a total of 5 times. And I'm looking for an exponential form here. 2, 2, 2, 2, 2. These are numbers. So normally, if it didn't say exponential form, I would just multiply 2 times itself 5 times, which is the same thing as saying 2 to the 5th, right? We have the same base as 2. 1 plus 1 plus 1 plus 1 plus 1 is 2 to the 5th. X's. X cubed, x cubed, x cubed, x cubed, x cubed. They all have that same base of x. If we add up those exponents, 3, 5 times gives us x to the 15th. And as I start thinking about this, I'm adding 3 to itself 5 times. Isn't that what it means to take 3 times 5? Yep. 3 5 times? And that's going to be the shortcut we look for here in a second. Last one in this row. So now we're going to have negative 2. Negative 2a cubed b to the 4th times 2a cubed b to the 4th times negative 2a cubed b to the 4th. We are cubing that. Once we get into these negative bases, it gets just a little more difficult, just a little. Because negative 2 times negative 2 times negative 2 isn't this. This is saying the opposite of 2 cubed. This is saying multiply 2 by itself 3 times and then multiply by the negative. What we want is this. Take negative 2 and cube it. Times. There's an a base. What is going to be the exponent on the a? 9. 3 plus 3 plus 3. There's also a b base. What's the exponent on the b? 4 plus 4 plus 4. 4 times 3, and we get 12. So having seen all of those, if we had x squared to the 40th, There's no way that I want to do x squared times x squared a total of 40 times, right? That would be the long way of doing it. So what would you actually do with the 2 and the 40 to figure out what this is equal to? Multiply them. We've seen it a lot of times. We'd have 40 of those 2's. 40 times 2 is 80. So essentially, you are multiplying them, and we get x to the 80th power. So when you are raising a power to a power, you're taking an exponent, some kind of power, to a higher power, you multiply the exponents. Blow it up. Take it to a higher power. Multiply those exponents. We don't have to do this expanded form every time. If you want to, if you're not sure, maybe it's a good check to refresh your memory or to give you some confidence in what you're doing. We can use this shortcut directly. We can just multiply those exponents. There's not a lot of rules, but there are enough rules where you're going to want to make sure you remember, when do I add these exponents? When do I multiply them? When you take it to a higher power, that's when you multiply. So first example here, x to the 5th to the 3rd. This would give us x to the 15th. Multiply them because we're taking it to a higher power. Number 2, we have 2 bases on the inside of the parentheses. This 4 is going to apply to both of them. X squared would multiply by itself 4 times. We take this 2 times 4, and we would get x to the 8th. And we do the same thing for the y. 5 times 4 is 20. So x to the 8th, y to the 20th. Was that a 3?
Yeah.
Oh, my poor handwriting. How about 3 times 4, 12? Look better? All right, number 3. A couple of steps in this one. First of all, evaluate this part. End of the 4th to the 3rd. End of the 12th. And then times end of the 5th. There's nothing outside or blowing this one up any higher. So we did the first part. Now we can take the end of the 5th. What do we do with the 12 and the 5 now? This is adding. This is what we looked at the previous day. We get end of the 17th. Number 4. This says parentheses 3x squared. That is not the same thing as 3x squared like this. These things are different. And the problem that we're looking at, the 3 is being squared and the x is being squared. 3 squared is a number, so I'm actually going to evaluate that. I can use my calculator or recognize that it means 3 times 3, which is 9. This problem comes out to 9x squared, as opposed to just saying that we're dealing with a problem like this. Again, different problems, because the whole 3x is in parentheses being squared. This is what we get. To number 5. The negative 6 is being squared, and the x to the 4th is being squared. I'm showing a little bit more work in this one because I know I'm supposed to multiply those exponents. So this end comes x to the 8th. But when you have a negative base, be careful with that. You're taking negative 6 squared. You're taking negative 6 times negative 6. And what's a negative times a negative? Positive. So this should be positive 36 x to the 8th. There's one more in this row. And now we have 3 terms inside of the parentheses. I'm going to start at the back because I think it's the simplest. So the y has to be squared. The x cubed has to be squared. X to the 6th. And the 4 has to be squared. So 4 squared means 4 times 4, and that's 16. Piece by piece by piece. These are all monomials on the inside. What we mean by that is there's no plus signs or minus signs separating the different terms. I can just distribute this to all the terms in there. All right, one more row in this set. And what do all 3 of these problems have in common? Fractions. Fractions sometimes make problems more difficult. I don't think so in this case. We just have a little bit more distributing to do. So in this problem number 7, the 3 is going to all of those terms. We're going to have 4 to the third, a to the third, over 5 to the third. I don't want to leave these numbers the way they are, so go to your calculator. Take 4 to the third. It means 4 times 4 times 4. We're seeing 64 out of that. So 64, a to the third over. And then take 5 to the third. 5 times 5 times 5. Because 4 and 5 didn't have anything in common, 64 and 125 won't either. There's our number 7. All right, to number 8. There's 2 terms. There's a numerator, there's a denominator. Square your numerator. Square your numerator, it becomes b to the 10th. Square your denominator, that makes it become 4 squared, which is different than 4 plus 4. It means 4 times 4, right? That's what 4 squared means. 1 times that 2 gives us 4 to the second. 4 to the second is 16. So there we go. Caution tape here, 10 and 16. This 10 and that 16, do they have anything in common? 2, right? So can we divide them both by 2? No. 16 is like a base. 10 is an exponent. There's nothing we can do to simplify those with each other, so don't even try it. All right, last one in this row, and it's right here. I want you to try it first, see what you can get. The 4 distributes to both terms in the numerator. It distributes to both terms in the denominator. B to the 4th, 2 to the 4th would give you 16. And the denominator, 3 to the 4th, is 81. C to the 8th, 16 and 81 don't have anything in common. And like we looked at in the last one, don't try to simplify those exponents with each other. B and C are different bases. There's no way to simplify those. So that's what we get. Here's the second part of our 6.1 day 2, looking at negative exponents. Negative exponents don't make negative numbers. Negative exponents move things. And we looked at that a little bit yesterday. Using the division rules on this first problem, we would take 2 minus 5 and get x to the negative 3. However, we don't want to leave a negative exponent in our answer, ever. And what we said is then that this would change into, instead of having x to the negative 3, it would become x to the positive 3 in the denominator. We want something in the numerator to hold its place, and so we just would put a 1 up there. So when you expand it out, you would see that x squared is x times x, x times x times x times x, like this. Then we would divide by x. We're left with 1 over x cubed, which is the same thing as I got from doing it that shorter version. This is the expanded out way in case I'm not sure. But when we're dividing these monomials, you subtract. And if you get a negative exponent, you have to move it. A couple of notes. X to the negative a could be like x to the negative 5, x to the negative 10. It doesn't matter. But if you have a negative exponent, you move it, and then it would become positive. So we see this quite a bit. We don't see this next one quite as much, but if you have a negative exponent in the denominator, then it pops to the top, and that's where it would become positive. So negative exponents, negative people bring you down, negative exponents move things down, or they might move them up. If you have a negative person being extremely negative, maybe it makes you move to the top. It's not a perfect analogy, but negative exponents move things. A few examples. Number 1, 7x to the negative 3. The negative 3, does it apply to the x? Does it apply to the 7? No, it's not like this, where the negative 3 would go to both of those terms. The 7 is fine where it's at. The x to the negative 3, that one has to go to the denominator where it becomes positive, and we get this. This problem is not terribly complicated, but because there's not a lot to do, this is a problem that trips people up sometimes. The 7 really has like a positive 1 there. That's why it gets to stay in the numerator. So number 2, another kind of tricky one. We look in the numerator, there's this negative 5. It's a negative 5 as opposed to being 5 to the negative 1. There is a difference. This is like negative 5 to the first, which is a positive exponent. So that negative 5 can stay exactly where it is. However, in the denominator, we have this a to the negative 4. We don't want the negativity. So what we're going to do is we're going to change the negative to a positive. And when you do that, you move it. So the a to the negative 4 that was once in the bottom now moves up to the top with the negative 5. And we have no more negative exponents. Notice the negative 5 didn't have to switch also. The negative 5 was okay to stay exactly where it was. Only the negative exponents have to move. Consider that in this problem number 3. There is a 2. There is an x. There is a y. And there is a z. Not everything has to move. To begin with, the 2. Does the 2 need to move, yes or no? No, it does not have a negative exponent. Does the x need to move? No. It does not have a negative exponent. Does the y need to move? Yeah. It has a negative exponent, so we move it, and then it becomes positive. Does the z need to move? Yeah. So it goes to the top, and now it becomes positive, and there's our number 3. Again, this can be a tricky problem. Look base by base. There's a 2, an x, a y, and a z. You have to take each of them individually. Number 4. Same idea. But I'm noticing something right away in this one. There's a 12 over negative 6. Those are different bases. However, we're still talking fractions here. We're still looking at dividing and simplifying and so forth. What goes into both 12 and negative 6? I can divide them both by 2. I can divide them both by 3. I can divide them both by 6. And 6 is the biggest, so divide by 6. Divide by 6. And those numbers are taken care of. I didn't have to move either of those because they weren't negative exponents. What do we think about the x to the negative 9? Got to move it. What do we think about the y to the 3rd? Leave it there. Doesn't have a negative exponent, so leave it there. As far as the answer goes, I can leave it like this. This one negative sign could actually, this one negative sign, I need to get just that out of the way. I could make it negative on the top, or I could make it negative out front. It'd still be equivalent to the thing that I had to begin with. I'll leave the negative down here for now, but know that sometimes that negative could be just switched up to the top, and that would be okay. Dividing by negative 1 is the same thing as multiplying by negative 1, right? Yeah. That's why we can do that.
Why wouldn't it just move
why?
Divide by negative 6 or divide by 6.
Number 5, we've got a lot of pieces. Your goal is to figure out what moves and what it becomes. So go piece by piece, move them. All right. Yellow. Does yellow move?
No.
No. Gray doesn't move. Yeah. Blue doesn't move. No. Pink doesn't move. Green doesn't move. C doesn't move. And we say multiplication is commutative. So if you had a to the sixth before y to the third in the denominator, that's okay. But these are the two things that need to be multiplied in the denominator. These are the four things that need to be multiplied in the numerator. But again, the order that you put them in the numerator doesn't matter. They need to have these numbers and they need to be in that location. All right, let's take a look at this next one. First glance, oh my, there's a lot here. Take it piece by piece by piece. It'll take a little bit longer, but this is definitely not outside of our abilities. We can do this one. To begin with, this is being taken to a higher power. When you take something to a higher power, what do you do with the exponents? Multiply. We have to multiply to both of those. So -2 times -4 makes that x to the 8th. For the y values, -4 times -4 is 16. Times, now I'll go to the back half of this one. This 2 also has to distribute. 2 times -1 is -2. 0 times 2 is 0. So using the higher power that we looked at earlier to distribute, to multiply those exponents, we get the green and red. Now we're looking side to side and we're multiplying these things. When they're in the same level like this, I'm not taking it to a higher power. Instead, now you add the exponents. Multiplying on the same level means you add the exponents. 8 plus 0 is 8. Y to the 16, y to the -2, add those. 16 plus -2 is 14. And there we have it. There's no negative exponents left over, so I'm not worried about moving anything around. That is my good and final answer. All right, a few more examples. These deal with fractions. We have a little more space to get these done. Same ideas that we've been working with. We're taking what's inside of parentheses to a higher power. So the -3 is going to multiply by both of those exponents. X is now to the -3. Y is now to the +18. So there's a 1 there. 1 times -3. -6 times -3. We have all this. Equals. Does the x have to move?
Yes.
It has a negative exponent. What does that mean? You have to move it down where it becomes positive. Does the y have to move?
No.
No, because it has a positive exponent. It can stay where it is. What about the numerator? It's got to be something. 1 is the placeholder. Number 8. There's a 2. There's an x. There's a 5. All of this is being taken to a higher power. All of this stuff has a bigger exponent. So multiply all of these numbers, all of these exponents that are there by -2. So we would get 2 to the -2, x to the -2, 5 to the -2. There's my first step. 3 bases, the yellow, the orange, and the pink. None of them had any exponents written, so there's an implied 1 for all of them. -2 times all of those gives us this. Can we have negative exponents in our answer? No. Does the 2 need to move? It's got to go to the bottom where it becomes positive. Does the x need to move? Goes to the bottom where it becomes positive. Does the 5 need to move? Goes to the top where it becomes positive. One more step in this one, because we have some numbers that are bases. We're going to have to do 5 squared. It means you're taking 5 times 5. You have to take 2 squared, 2 times 2. Then the x squared stays where it is. We'll pick one of these last problems. Number 9 it is. As is the case in a lot of math, we can do it in more than one direction. Here's what I'm going to do. I see that there's 2 terms in the numerator, 2 in the denominator. But before I raise it to the -1, could we simplify the inside first?
Yeah.
That means actually less work for us in the end. These 2 have the same base. What are we supposed to do when we divide? Subtract. What's 2 minus 3? So a is to the -1. And then those b's both have the same base. 4 minus 2 is 2. So we simplified the inside. There's not as much stuff in there now. And this is being taken to the -1 power. Because it's taken to a higher power, this is when we multiply those. -1 times -1 is 1. For the b values, 2 times -1 is -2. Is a to the 1 okay? Sure. Is b to the -2 okay? No, the negative has to move. Where does it move? To the bottom, where it then becomes positive, and there we get a over b squared.